Now that we familiarized ourselves with the concept of Lewis structures and formal charges in Lewis structures, we'll talk about a related concept in structural chemistry, and that is resonance. The easiest way to encounter resonance is to start drawing a series of Lewis structures, and at some point we'll realize that certain molecules have multiple reasonable Lewis structures. For example, if you look at this cationic system, we can imagine that these electrons of nitrogen move into this single bond, and we'll denote this by this curved arrow. And what this movement will produce is now a double bond between carbon and nitrogen. The lone pair of nitrogen is gone, and now the positive charge moves onto the nitrogen, because if we again count the formal charges, we'll see that carbon now is neutral, but nitrogen is positively charged. Now the question is, well, which one of these two structures is correct? And the answer is, they're both correct. In other words, the true molecule exists somewhere between these two structures. So the bond between carbon and nitrogen is neither single nor double, but something in between. And also both carbon and nitrogen share this positive charge. This state of molecule is called the resonance hybrid, which simply means that this molecule exists in a form which is somewhere between the two extreme structures drawn between these brackets. And in this structure, the positive charge is delocalized between the two atoms, which makes it stable, since nature doesn't like concentrating either positive or negative charge in a single spot, but rather spreading it out over as many atoms as possible to minimize its reactivity. Now the concept of resonance is a little daunting at first, but I think an interesting analogy to consider is the analogy of a unicorn. So unicorn, if it was really an animal and not just a mythical creature, could be considered a resonance hybrid between a horse and a rhino. And that would not mean that the unicorn exists half of its time as a horse and the other half as a rhino, but it indeed exists as a single animal, just composed and sharing the properties of both of the extremes. The same case applies to resonance hybrids as well. Resonance is actually a very commonly encountered concept, and I will give you a number of other examples. One of them is the acetate anion, so the anion that results after deprotonation of acetic acid. And if we deprotonate the acetic acid, one of the oxygens has a negative charge on it. But we can easily move this charge back between carbon and oxygen and move this one over here, which will now result in a different structure. So this oxygen will have a negative charge, whereas the bottom one will have a double bond to carbon. Okay? And here the true structure of an acetate anion is again somewhere between the two extremes. So both oxygens have a little bit of a double bond, but not quite, to carbon, and both of them have a little bit of negative charge. So the bond order in the CO bond is 1.5. Okay? Now both of the molecules that I drew so far are charged, and the resonance is often encountered in neutral molecules, but even in neutral molecules you can sometimes see parts of molecule being positively or negatively charged. For example, if we look at nitromethane, which is a very common solvent in organic chemistry, its structure is somewhat resemblant of an acetate anion. Of course, we have nitrogen here, which means the nitrogen will have a positive charge on it. And overall, the molecule is still neutral, but it does have first formal charges on its atoms, and it can also exist in two different resonance structures. So this would be a molecule of nitromethane. The example of acetate anion and nitromethane features two resonance structures which are clearly identical in everything except their orientation. And so it's reasonable to assume that those two resonance structures are sort of 50-50 contributors to the overall resonance hybrid. But let's look at some molecules where this does not necessarily have to be the case. For example, the first molecule that we drew is this cation, which has a positive charge on carbon, and then neighboring nitrogen. And its other resonance contributor has a double bond between carbon and nitrogen, and a positive charge on nitrogen. The important question to ask here is, are these two equal contributors? Answering this question is important because the properties of the molecule will depend on whether these two are 50-50 or 90-10 or 99-1. In other words, the contributor which is more important will sort of dictate the properties of the molecule, and the molecule will look more like that specific contributor to the overall resonance hybrid. So if we look at these two structures, we'll notice that this carbon does not have an octet. It only has a sextet of electrons, which makes this resonance structure somewhat unfavorable, and this is a minor contributor. This one, on the other hand, is a major one, since all elements have filled up electron shells. Another example could be formaldehyde, a very simple molecule which has a double bond between carbon and oxygen. This is its neutral structure, but it could easily be drawn in this other resonance structure where oxygen now has negative charge on it and carbon has positive charge. Again, carbon here doesn't have an octet, and so that is one problem with this structure. The other problem in this structure is that there is charge separated. And as we know, positive and negative charge don't like to be separated, they like to be combined. So clearly this contributor is the minor contributor to the overall resonance hybrid. But it still determines the properties of formaldehyde to some extent, because this structure is very polarized. There is a negative pole and a positive pole. And there, as we know from experimental data, there is some dipole moment in formaldehyde. And that is significantly contributed to by this minor resonance structure. There are some general rules that we will now cover as to how to to practice drawing good resonance structures. And I will give you those rules. So the first one is they must be valid Lewis structures. So Lewis structure concept is sort of an overarching concept, and so it takes preference over resonance. So any reasonable resonance structure must also be a good Lewis structure. The second rule is only move electrons. You notice that in all the resonance structures that we drew, electrons were moving, nuclei stayed in their places. And if your nuclei move, then you no longer have the same molecule, and so you cannot talk about resonance structures anymore. The third rule that we did not encounter, but it is important, is that the number of unpaired electrons must remain the same. Finally, an important concept here is that we must have octets on all atoms. We must minimize charge separation. As we've seen in the molecule of nitromethane, we cannot eliminate it completely, but that's okay because we minimize it, and it's the same in all resonance structure. And one thing that is sort of intuitive is to put negative charge, if we can, on electronegative elements. And conversely put positive charge on positive elements. The final concept, which is an important one, is that of delocalization, and we will come back to this multiple times in this course, as we will to the concept of resonance. And so to reiterate it once again, delocalization is spreading out of positive or negative charge over more than one atom. It's a stabilizing concept because nature does not like concentrating positive or negative charge in a single spot, since such a concentrated charge very strongly attracts the opposite charge, and that makes it very reactive. Conversely, if it's delocalized, it's stabilized, less reactive, and simply put, better, energetically lower.